Okay, one of the things that we often study in calculus is rates of change. In fact, the actual calculus itself is essentially a study of change. And one of the examples that we generally use to start out with is using something that we know quite well, which are speeds or velocities. And what we're going to start out with is this idea of average speed. We know that if we are going down the highway at 70 miles per hour, okay, that if we had a cruise control set, we could certainly keep it at 70 miles per hour. But if I were to say that I'm going to drive from here to Detroit and I averaged 70 miles an hour, does that mean that I went actually 70 miles an hour for the whole entire time and never changed from that? I mean, obviously we're going to start out at 0, so we're going to have to accelerate and then decelerate once we get there and so on. Okay, but if my average speed is 70 miles per hour, okay, what the average speed is taking into account here is just how many miles I went divided by how many hours it took. Okay, so the average speed is ultimately going to be a calculation of change in distance over change in time. Okay, so in general, okay, that is going to be any average speed, or more generally, average rate of change. Okay. Now, here's a question that we're going to pose: is if I were to, let's say, take a rock, okay, and I want to drop it off a cliff, okay, and I want to know how far, or not how far, but how fast is what is the average speed of the rock after 2 seconds, okay? Well, ultimately, I'm going to use this equation. We'll kind of get to the gist of why this is the equation later, but this is going to be my equation, okay, for distance versus time in this situation. And anytime that we're dealing with feet per second and we're on the Earth, okay, the distance equation is going to be this y equals 16t squared. Okay. So with that said, if I know that this is my equation that I'm going to use to find the distance after a given time, if I were to put a particular time in there, like 2 seconds, then I'm going to go 2 squared, it's going to be 4 of course, times 16 is going to be 64. So that means the position is going to be 64, that's the change in position, and the change in time is 2 seconds, as I mentioned. And so therefore the average speed of the rock will be 32 feet per second. Okay. All right. So again, if we're near the Earth's surface, this is going to be our equation for the distance traveled for any object that's in free fall. Okay. And once we drop a rock, it's in free fall. Fair enough? Okay. All right. But again, ultimately the change in distance, okay, 64 over the change in time 2, okay, is going to give us our average speed. Now, I want you to take a look at the graph that I have drawn here. It's a graph of a parabola. Okay, and in terms of from a graphical standpoint, what did I really just find there when I did my 64 over 2? Well, knowing that the y equals 16t squared curve is a parabola, okay, it's got the vertex at 0, 0, and if I start out at 0, 0, okay, and again keeping in mind that t represents time, y represents distance. So at 0, 0, my distance is 0, time is 0. At time 2, the rock is at 64, so I'm at this point right here. So looking at the graph, and then looking at my calculation over here to the left, okay, what have I just calculated here for this particular set of 2 points? Okay. If I do the change in distance, which is the y-coordinates of this thing, and time is the x-coordinates, okay, what have I just calculated if I do a change in y over change in x? Okay, what does that tell me about this line segment that I have drawn that connects these 2 points? It's the slope, isn't it? Okay. So ultimately, that average speed is essentially a slope between 2 endpoints. Fair enough? Okay. Because if we were to draw the graph of the equation in question, okay, the slope that connects the 2 endpoints in question, okay, is the average rate of change. The change in y over the change in x is the average rate of change. Okay? And in this case, it represents some speed. Okay? Now, I'm also going to mention that when we're dealing with a problem, a free fall problem. The other equation I have here, this is just an equation that we use when we're dealing with meters per second squared. So depending on what the context of the question is, if the units are in feet, okay, then we're going to be using this equation. If the units are in meters, then we'll be using this equation. If they were in something other than those, then they would give you the equation. Okay, so just knowing that, just so you recognize which equations go with which. Okay. All right, now one of the questions that we want to pose next is if I can calculate, where the object is at different times. And again, I'm just using just an example of 2 seconds just to start somewhere. Okay, my next question would be if that's the average speed of the rock, okay, on its 2-second travel, if you will. Okay, what's the speed of the rock exactly at 2 seconds? Okay, because ultimately when I drop it, if it's in my hand still, how fast is the rock going? 0. Okay, if I drop it, okay, at 2 seconds, it's got some kind of speed to it. Right? Because what force is acting on it? Gravity. Okay, and so whatever that speed is, okay, and knowing that with the way gravity works, okay, as the object falls further, the object accelerates. True? So is the 32, is this the speed of the rock at time 2? And the answer is no. This is just the average speed of that 2-second journey. Okay, so the actual speed, okay, at that point, 264, if you will, is something that we're going to learn how to find now. Okay, so if you take a look at my second picture here, and what it boils down to is that earlier, I'll kind of redraw what I had here, and I'll make it a little bit exaggerated. Okay, if I take the two endpoints and I find the slope between them, okay, ultimately that gives me a change in position over change in time. It gives me some speed. Okay, and if you look at the curve itself, okay, the curve itself at that particular point, okay, looks much steeper than the actual line I have drawn here, doesn't it? So we would expect that the answer here, the real answer, has got to be more than 32 then. True? Based on this particular curve. Okay. Seeing as how at that point, that curve is definitely steeper than the line I have drawn. True? So instead of using 0, 0, and 264, okay, to try to figure out the slope at that particular point, okay, what if we used a different point, like 116? If we used 116 in 264, now look at that slope. How does that slope compare to the previous slope? Steeper. True? So if it's steeper, but still, is it as steep as the actual curve at that point? So if that's not good enough, then what if I used 1.5? And I made a point 1.5, whatever, in 264. Wouldn't that give me even a better estimate of what the slope is at that point? Okay. So if 1.5 is better, then what would be even better than that? 1 3/4, etc. And ultimately, what would be the best? Okay. How close would I want to get my other point to 264? How close would I want to get to it? I mean, if I used 1.99999, that would be good, but what would be even better? 1.99999, another 9. True? So what we're getting at here is that if I could get that point really, really close to that 264 point, okay, I would have a line that essentially showed the slope of the curve at that one point. Okay, and I have that drawn here. That's what we call a tangent line. So if this is my point 264 here, okay, and I want to figure out what's the slope of the tangent line at that point, okay, question is, what do I do? Well, that's what we're going to develop. We're going to develop a method to do that today. Right? Because if you think about it, the only way we know how to calculate a slope is to have 2 points. Okay, if we only have 1 point, the slope formula doesn't work, does it? Okay. So here's what we're going to do. We're going to, again, start with our point in question. In this particular case, it's 264. Okay. And then we're going to pick some other arbitrary point that's either, it could be to the left of that point or it could be to the right. It really doesn't matter which side of the point it's on. Okay. But ultimately, if I go either to the left or to the right, and I go h units to the left or to the right, I put mine on the right so I could use 2 plus h. Okay. And if I use that 2 plus h, okay, to represent this point right here, keeping in mind that our starting point being 2, h is the x distance, if you will, the horizontal distance between those 2 points. So that point right there that I drew is going to have coordinates 2 plus h, okay, and the y coordinate, of course, is going to be f of 2 plus h. Now, in our particular case, we know what f is. F is 16t squared. Okay, so we could really just write this as 16 times 2 plus h squared, which we will in a minute. Okay, but in general, I'm going to list my x coordinate of a point that is close to 2. Okay, and the y coordinate, of course, is that x plugged into the equation. Okay, whatever the equation may be. In this case, like I said, we know the equation. Okay, and so you'll notice my second step was, instead of writing f of 2 plus h, I actually put the 2 plus h into the equation that we were given. Okay, because we were given that equation, y equals 16t squared. Okay. So at this point, we have 2 points. And remember, what do we need to calculate the slope between 2 points? We need the 2 points. We got 1, we got 264 here, and then we have 1 that we have an expression for. So it's not as nice as 264 because it has a variable in it, but it's still an expression for a point that's arbitrarily close to 264. Okay. Now, ultimately, again, if those are our 2 points, and we want to calculate the slope between them, we're going to use our slope formula. So if I consider this my second point and this my first point, I'm going to write it down as the change in y over the change in x. So there's my slope, my y2 minus y1, and in the bottom I got x2 minus x1. Now, if you look at the bottom of the equation, you can see that there's something that we can do to simplify that. If I have 2 plus h minus 2, what happens to the 2's? Oh, they're gone. Okay. So we have now, and I'll leave this part for a minute, but again, this gives me an expression for the slope of this curve at the point 264. Now, what we want to have happen here is we not only want the slope, but remember, what do we want h to be like? Because we said we wanted these 2 points to be how close to each other? Yeah, as close as possible. So in other words, infinitely close. Okay, we want them to be infinitely close, and this is where the idea of a limit comes in. Because ultimately in this expression, okay, what do we want to let h be equal to? What are the x distance between these 2 points? We want that distance to be closer and closer to what? 0. Okay, and so that's exactly what we do. We write it as a limit. Okay, we want to find the limit of this expression as h approaches 0. Okay, and what this is going to do for us, okay, is it's going to give us, okay, the slope of this curve at 1 point. Now, which is kind of a little bit profound for us because in the past all we've dealt with in terms of slopes is slopes of lines. And if I have a line, does the slope change? No matter where I am on the line, the slope is the slope. The slope is m. True? But when I have a curve like a parabola, at every point on the curve, the slope is what? It's different. Okay? But what we're doing with this idea is we're finding, okay, the slope at a particular point for a curve instead of a line. Okay? Which, like I said, is fairly powerful, more so than other stuff that we've done. So, who sees the problem here? If I want to figure the answer to this out, if I want to evaluate this limit, what's wrong with it? Yeah, I can't have 0 on the bottom. We got a direct evaluation issue, don't we? But similar to that one that we did, the 2 plus x cubed one, okay, we can see that if we do some algebra here, we might be able to manipulate that top and get that h out of there. True? So that's exactly what we'll do. We'll go ahead and expand the 2 plus h. So 4 plus 4h plus h squared. Distribute the 16. And then notice what happens. The 64 or the negative 64 are going to be gone conveniently. True? Because what do the 2 left have in common on top now? They both have a what in them? They both have an h. So notice what happens if we factor out the h from the top. I can take that h and get rid of them. Okay, now I have an expression of 64 plus 16h. And if I have that, now can I directly evaluate? Yeah, absolutely. Okay, and so therefore the answer is 64 feet per second. Okay. And keep in mind why the units here are feet per second, because again, this comes from a slope. And what is this measured in? Okay, these are the y values of our curve. The y values are measured in distance, in feet. Okay, h is the change in t, which is time. And so notice the expression is still in a ratio of feet and seconds. So therefore, feet per second is still our unit, just like it was for average speed. Okay, what we've calculated here is what we call instantaneous speed. Okay, we found the slope of this curve at this point. Okay, which again, depending on where we're at on this curve, is going to be different at every point. Okay. Just taking a look at the rest of the curve up here. Okay. If we look at knowing that the instantaneous speed, okay, is the slope of the tangent line, if you will, okay, what would we expect to be the slope of the tangent line here at 0, 0? If I were to draw a tangent line here at the vertex of that, okay, wouldn't that have a slope of 0? Okay, it would indicate an instantaneous speed of 0. Does that make sense in the context of the problem? At time 0, how fast is the rock going? 0. Now, in this physical problem, it wouldn't make sense to talk about the left half of the parabola, because the left half of the parabola would mean time that was back in time, if you will. Okay? And ultimately, our experiment starts when what happens? When we let the rock go. Okay? But again, if you think about it, what's going to happen as time passes? If we wanted to find the instantaneous speed at 4, okay, we should expect that the answer would be more or less than this. And more. Okay? Because the longer the rock falls, the faster it's going to go. And does that make sense in terms of the picture? Because we know about parabolas. As parabolas go off to the x, they get even more and more steep, don't they? Which more steep matches up with a bigger slope value, doesn't it? Questions so far? All right, let's check out another one here. If we did something like, I want a similar situation, just to go through the steps again to make sure we're clear. If I do the other parabola, the meters per second one, and I want to know what's the instantaneous speed at 3. Okay. So the equation again is 4.9 t squared. And I want to know what's the instantaneous speed, okay, of the rock at time 3. So knowing that we need 2 points, let's find the y coordinate first. So if I do 3 squared, that's 9. And I need, what's 9 times 4.9? 44.1, right? Okay. So 344.1 is that point. All right, and if I want to find the slope at that one point, I need to make another point, an arbitrary point, that's h away from that point. So what are its coordinates going to be? 3 plus h. Whoops, I don't want that there, comma, sorry. And then the y coordinate of 3 plus h is going to be, in general, f of 3 plus h. Because ultimately we're doing this with a couple of parabolas for our examples here, but this can be done with any curve. Okay, it doesn't matter whether it's a cubic function, it could be an exponential function, it could be a trigonometric function, okay, whatever the case may be. Okay, we start with polynomials because the algebra is the easiest with polynomials. Okay, but the concept is exactly the same. So help me with this part. Particularly our f is 4.9 t squared. So that means I'm going to write what? 4.9, 3 plus h squared. And is it ever going to be right if I don't put parentheses around 3 plus h? So we need to have that. All right. Questions on how to get the 2 points in question? Okay. Then from there we set up our slope. So 4.9, 3 plus h squared minus 44.1, 3 plus h minus 3. We do my change in y over change in x, y2 minus y1, divided by x2 minus x1. And let's go ahead and distribute. We'd have 9 plus 6h plus h squared. And on the bottom, once again, we find h. And if you think about it, no matter what we pick for our curve, okay, or what point we choose, isn't the bottom always going to be h? I mean, we're always going to have a situation where it's going to be a plus h and then a, right? So it really doesn't matter what curve it is or what a value it is. In this case, it's 3. In the last case, it was 2. Okay. So, with that said, and what are we hoping that the answer to this is right here? And we already know it is because we did that a minute ago. Why do we want it to be 44.1? Because we want this one to be gone. Okay. And so let's go ahead and do the math. So 44.1 and 4.9 times 6, 20.4. Okay. And then 4.9h squared minus 44.1, space, sorry, all over h. But once again, those 44.1s cancel like we were hoping. If we factor an h out, we get 29.4 plus 4.9h. And just like the last time, and just like will happen every time, the h's can go. And so we're left with the expression of 29.4 plus 4.9h. Now, remember I didn't write it yet, but ultimately this would be an expression for the slope, okay, at this particular point. But what do we want h to be? We need to know what that expression equals when h approaches 0. Okay, because we want the h, the distance between our 2 points, to be infinitely small. Okay. And so what's our final answer then? 29.4, and what are the units? Meters per second. Okay. Questions? All right. So the good news with this is that this is an introduction to a lot of the stuff that we're going to be working on throughout the first semester, okay, throughout the first part of calculus, chapters 3 and 4 in particular. Okay, and from here, what we're going to do is the second half of our homework assignment. We're going to have a little bit of time right now.